My name is Chinyere Ugizi. I am the curator of Dreaming New Worlds. It's a project of the Goethe Institute, the German Cultural Center in Nigeria. The main objective of the project is to encourage a multidisciplinary approach to science and arts collaboration, especially in Nigeria, because in Nigeria and Lagos. And so with you all, and in the audience is the School of Science and Technology at Pan Atlantic University. I am so geeked to have you guys here. I actually went to PAU, but I was in business admin. And the closest we had to science students was ISMS. And I used to disturb them. So like having engineering students, I was like, if I was here, oh good. Well, yeah, I'm glad you guys are here. And then we also have artists and other creatives from across Nigeria and the world. The current cohorts for this year's edition, because we had an edition last year. So this year's edition of Dreaming New Worlds, they're also here. They're also artists, and they feel that we're using their skills, their technical skills, to create immersive arts across different practices. So you can get to talk with them and exchange ideas between the two of you. And here is Ife. Ife is your XR extended reality body. Last year, he won our first ever, because Dreaming World is a partnership with Studio Quantum. Studio Quantum is a project with Goethe Island, Mexico, Johannesburg, Brazil, Nigeria, Johannesburg, South Africa. So we take artists to Ireland to learn about how to use quantum computing, and America, San Francisco. And last year, Ife, who experiments with extended reality, looking at our cultural heritage, got to go to Ireland to push forward his practice with quantum computing, and he's been experimenting with it ever since. So this is sort of like a give back. He's currently in Berlin on another residency, still working on his craft, and he's just here to teach us all he has learned, how you can make use of this technology for your own individual projects. And yeah, I'm happy you are here, and I'll give you the floor now to Ife.
Hi everyone, good afternoon.
Yeah.
All right. It's so glad to be here. I'm so glad to be a part of Dreaming New Worlds, for the second year. Last year I attended the exhibition, and it was really amazing. And so I'm glad to be a part of this year's session. So I will share my screen now, and just give me a moment. All right. So the title of my presentation today is Dreaming in a Quantum World. And first of all, who am I? My name is Ife, or Skodo-Lee. I am a 3D environment artist, XR developer, and creative technologist. Like Chinyere said, I was the Goethe Institute Studio Quantum resident artist for Lagos and Dublin. And I'm currently the Special Affairs Artist Resident for Basel. And during my residency in Dublin, I got to meet like lots of people, like quantum physicists. So this year is Alessandro. He was my instructor in quantum computing. He taught me how to like program quantum computers. And beside me is Edie Fong. She was also a recipient of the award, but ours was in San Francisco, but she lives in Ireland, so she was in Ireland about the time I was about leaving, so we met up. These were the guys at Trinity College, Dublin, and they were also quantum researchers, and with them I was able to, I did like some crash courses in like quantum computing in one of the offices.
All right. For instance, if this is the spin pointing up, this is the spin pointing down, we could have a state which, if we correctly normalize it, it will look like this.
So that was just a short clip. So that's Felix Binder. He's also a quantum physicist in Trinity College Dublin. And so with that, I was able to because I have ideas and see how I could actually bring to fruition. I'd always been interested in quantum physics for a very long time. Right from secondary school, I always loved physics a lot. I found it far more fascinating than chemistry. Chemistry always was very abstract to me, but physics was. I could feel and have an intuition for it, so I could feel the forces and all like that. But unfortunately, or fortunately, I didn't study physics in university. I actually did study architecture. But then after my architecture degree, I got down the rabbit hole of trying to learn more about modern physics. That was quantum physics, general relativity, string theory, and all of that. So the opportunity came last year to actually experiment with all that I found fascinating and all that I learned so far and use it in a project. So my topic today, or my talk today, will start from like the basics of quantum computing, right? But before I start, I would love to read this excerpt for you to sort of gear your mind towards how you probably might want to think about the phenomenology of approaching it, in a sense, especially for people who are like us, who are not experts per se, but who find it very interesting, but also have interesting ideas. So this was an article by Paul Dirac. He was a Nobel laureate, like one of the youngest, like at age 24, if I'm not wrong. Brilliant mind. And this was called from the article called The Evolution of the Physicist's Picture of Nature. It was a 1960 article from Scientific American. So I'll just read for it. So I might tell you the story I heard from Schrödinger of how, when he first got the idea of this equation, he immediately applied it to the behavior of the electron in the hydrogen atom, and then got results that don't agree with experiments. The disagreement arose about that time. The disagreement arose because at that time it was not known that the electron had a spin. That, of course, was a great disappointment to Schrödinger, and it caused him to abandon the work for some months. Then he noticed that if he applied the theory in a more approximate way, not taking into account the refinements required by relativity. So this rough approximation of his work was in agreement with observation. He published his first paper with only this rough approximation, and in that way, Schrodinger's wave equation was presented in the world. Afterwards, of course, when people found out how to take into account correctly the spin of the electron, the discrepancy between the results of applying Schrodinger's relativistic equation and the experiment was completely cleared up. So I think there is a moral to this story, namely that it is more important to have beauty in one's equation than to have them fit experiments. If Schrödinger had been more confident of his work, he could have published in some months earlier, and he could have published a more accurate equation. The equation is now known as the Klein-Gordon equation, although it was really discovered by Schrödinger.
Okay.
And in fact, it was discovered by Schrödinger before he discovered the non-relativistic treatment of the hydrogen atom. It seems that if one is working from the point of view of getting beauty in one's equation, and one has really a sound insight, one is in a sure line of progress. If there is not a complete agreement between the result of one's work and experiment, one should not allow oneself to be too discouraged, because the discrepancy may well be due to minor features that are not properly taken into account, and they will get cleared up with further development of the theory. And so this is a way of thinking about quantum physics. Is someone speaking? Okay, so this is a way of thinking about quantum physics in a way that relates to artistic interpretation. So artistic interpretation, and the fact that sometimes you have to go a particular route because of how beautiful it is, and you shouldn't worry so much about experiments, conforming to experiments so much, that beauty might be a way of actually, might be a clue that you're on the right track. And so with that, I begin. So what is quantum mechanics? So quantum mechanics is the physics that describes the properties of particles on the atomic scale. That's basically what quantum mechanics is. And to kind of explain what quantum mechanics, how it works, the very famous experiment is called the double slit experiment. And so before the 20th century, there was always debate about what the nature of light was. So there was the thought of light being a wave, or light being a particle. And so there was an experiment that was conducted whereby electrons from the atom. So the atom is made up of the electron, which orbits around the nucleus, and the nucleus has the proton and the neutron inside, right? So so electrons were fired, and if you fire the electron like through these two openings here, the expectation is, okay, yes, you fire the electrons, and it forms this pattern on like a blackboard behind you. That's what you expect, two separate patterns. But once the experiment was conducted with electrons, and by then electrons were thought of as particles, just particles, right? This was in fact what happened. So this is an illustration from CERN. And so what actually happens, it's not two separate, what's it called? You don't get two separate, pieces of electrons on two sides. Rather, the electron creates what we call a diffraction pattern. So this is what happens to the electron. It creates this pattern here. Okay, I think it's a better explanation. So it creates this pattern here, and this pattern, for people who are done, who are aware of patterns in physics, this is the pattern you get when an object is a wave. And it was very confusing that something that we thought of as a particle was acting like a wave. Then the next step of the experiment was, okay, probably the electrons were, interfering with themselves, and so they were kicking themselves, in one way or the other. So that's what caused this pattern. So what they later did was they started firing the electron, like one electron after another. So instead of firing all the electrons at once, they fired, individually, bam, 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 bam. And each time they still got this pattern, which was really mind-blowing, which meant that it wasn't the electrons, the total electrons acting on each other that caused the pattern, but it was the electron itself that was behaving as a wave. So which leads me to quantum concepts. So what are the concepts in quantum mechanics? The principal concept in quantum mechanics is the quantization of energy. It means that every particle either absorbs or emits a particular amount of energy, or a multiplication of that amount of energy. So if an electron wants to, so there's what called electron state, an excited state. And if an electron is excited, it means that it has absorbed some energy, and it can only absorb, for instance, an electron can only absorb, let's say, 2 joules of energy, for instance, right? And so if you want to go to the next state, that's to absorb 2 times 2 joules. If you want to go to the next state, that's to absorb 3 times 2 joules. So it's in quantum, it's in quanta, right? So it's in discrete levels of energy. You can't, and that flows around quantum mechanics. It even happens with things like spin, and I'll talk about later. So it gets back to what you call quantum superposition. So quantum superposition is an idea that so quantum superposition is an idea that that an atomic particle, an elementary particle, could be in multiple states at the same time, and it is usually expressed by what you call the quantum, by a spin. So you think of a spin as the Earth rotating, right? So if it's rotating clockwise, right, that is that's spin one. If it's rotating anti-clockwise, it's spin two, and there can only be two spins. There can't be any other spin. But in quantum mechanics, right, an electron, until the particular moment that is measured, is in both states at the same time. So it's both spin up and spin down at the same time, and everything in between, until the exact moment that the electron is measured. Then there's what's called quantum entanglement. Quantum entanglement means that two particles, two electrons, have information that is tied together. So if, for instance, and it's called spooky action at a distance, because according to general relativity, nothing can go faster than the speed of light, right? However, if you put two electrons, let's say 100 light years apart, right? If they are entangled, if those two electrons are entangled, the moment you measure the spin of one electron, you know the what's it called? You know the spin of the other electron, because they're quantumly entangled. So if one electron, the electron on Earth is spin 0, immediately you measure it, you know that the electron in the other side of the universe is spin 1, and that's what quantum entanglement. So there's also the wave function and Schrodinger's equation. I'll probably leave that. But wave function is basically how quantum particles are expressed, because it's an expression of probability, because an electron, so an electron can only be, you can only know the electron's position, or you can only know is the electron's velocity, but you can't know both at the same time. I think that's Heisenberg's first principle. But based on this wave function equation, you can then know you can know the probability of the state of this particular wave. Then quantum tunneling simply means that an electron can overcome barriers that you expected not to overcome. It's kind of like saying there's a door in front of you, but because of how excited the electron is, how excited you are, you can sort of teleport to the other side of the door without opening the door or anything of that sort. And so quantum mechanics sort of makes us challenge the very notion of reality as we see it, and it isn't like the Hegelian notion of thesis, antithesis, and synthesis, that then when there's thesis and antithesis, and once they come together, they sort of resolve from an antithesis. That's not what's happening here. It's a notion that these contradictions or seemingly contradicting things are inherent, and they are happening simultaneously. Like because when you think about it, how can an object be up and down at the same time? That's one of like those mind-blowing things of quantum mechanics that you see. And so from here we begin to talk about the idea of it from bits. So this is an idea by John Wheeler. So John Archibald Wheeler was like an amazing physicist. He was friends with Einstein, Niels Bohr. He was also like a teacher to people like Kip Thorne, Richard Feynman, and like really every task in the physics in physics, right? And he thought about how to relate quantum mechanics to information, which is something very fascinating because we live in a digital age now, and a lot of things we do are based on bits. A lot of things are based on bits. So it basically suggests that every physical object fundamentally arises from information. The way it's explained sometimes, it's there's a game called 20 questions, right? So if you the 20 question game works that, okay, the person asking the question as an object, let's say a dinosaur that he has in his mind. So the person that wants to find out needs to start asking questions that, oh, is the object big? Then the person.
Sorry, if I can you just give us Just give us a short technical break to change audio.
Okay, that's cool.
Okay, I can speak.
Yeah. Can you hear me?
Let him try speaking. Let's see.
Can you guys hear me?
Is he talking?
Hello.
What's the name? Digital audio.
Also, changing it to the default. Yeah,
If I could you speak now?
still not working.
Can you hear me now?
Try the other one.
If I can I speak again?
Okay, can you hear me?
Yeah, it's loud and clear.
Okay, that's good.
Okay, you can go
Yes,
ahead.
can I continue? All right, that's great. Okay, so like I was saying, first questions asked whereby the person asking who has the answer to the question, you need to
1
keep
second,
asking
if I,
questions.
you have to go back again.
Line in.
Can we try again?
All right, can you hear me?
Yeah.
Better?
Yes, it's better.
Yeah.
All right. Okay, so I was talking about 20 questions, right? And so there is someone who has the answer, and the person and another person wants to find out what that answer is. And the person who wants to find out keeps asking questions, right? That's is it big? Is it extinct? Is it does it fly? These are questions that are yes or no questions. And with that, the observer or the person asking the question can kind of narrow down exactly what that object is. However, John Wheeler brings up an inverse to that game, whereby the person who is meant to have the answer to the question actually doesn't have an answer, right? But with the but the person doesn't have the answer, but the person asking the question doesn't know that the owner of the object, right, doesn't have that answer. So the questionnaire keeps asking questions, and the owner, right, who's the person, I will call the owner the person who has the idea of what the object is, keeps randomly saying yes or no's. And based on the randomness of that yes or no, there begins to form an image of what that thing could be, what that object could be. And once the questioner finished asking the question, the object that fits into all those yes or no questions is created. And that's what John Wheeler says how the universe acts, that what we are doing as human beings, as observers in the cosmos, what we are doing, we're asking the universe and asking the cosmos questions on the fly, and the universe on the fly is creating the reality that we live in based on the yes or no questions that we ask it. And which is a very fascinating thing. And it goes into ideas of simulation theory about, is the universe like a big computer that sort of computes the whole that sort of competes reality as we see it and as we know it. And also theories that, it's possible that we can get physical and tangible things, like really tangible things, but because you have to imagine it, like you can generate tangible things by the ones and zeros of your computer. Not a simulation, but but tangible things by just ones and zeros, which is like really a really fascinating concept. And so we get to what we call to quantum spin. So quantum spin is property of quantum particles that give them a sort of intrinsic rotation. Like I said, there are only two spin states, spin up and spin down, and every particle is in a solution of both states until it measures. Until it is measured, then it picks one of the two values. So this is an electron that has what you call a spin half. So every quantum particle has spin, and it is an integer or it's a multiple of half. So it's either what's it called? So it's either what it's spin half, or spin 1, or spin 1.5, or spin minus half, or spin minus 1.5. But it's a multiple of half, right? So so let's talk about the electron and spinor particles. So the question is, if you're an electron, and by how many degrees would you need to rotate to get back to the orientation you started with? So let me escape here a bit and let me just get to my drawing board. So this is the question here. Let's say you're an electron and you're facing this direction. And the question is, how many degrees would you need to rotate, right, to get back to this state? So normally, what you would expect is a 360-degree rotation, right? So you start here. So you start here and you rotate here, and that's what you expect. But that's actually not what happens to an electron. If an electron makes a 360-degree rotation, what happens is it flips to the other direction. It goes in the other direction. So for an electron to actually get back to the direction it was before, it needs to spin twice. That's 720 degrees. So it will have to go like this. This is kind of like a crude way of putting it. And then if it spins by 720 degrees, it gets back to this state. And so particles like this are called spin half particles. And a way of illustrating it, I'll just show some videos there, because it's a really fascinating idea of you being able, you having to spin to rotate twice for it to get back to the point where you started. And so it's really illustrated by a Mobius strip. So I'll play this video to you guys. And that's it. And that's what an electron does. Whereby it has to spin twice. And what it does is and so it spins twice 720 degrees for it to get back to the state that's in. And so once you have things like this, you can start creating things like fascinating art objects. So this is a McLean bottle, and a McLean bottle is made from 2 Mobius strips. And the Mobius strip is made from basically a cylinder, right? But you turn the cylinder in the other direction, and then you point them together, and then it forms one continuous surface. But then a McLean bottle is a Mobius strip that is then joined together. And one of the fascinating things about the McLean bottle is that a McLean bottle is actually a 4-dimensional object. But what we see in the real world for a McLean bottle is a 3-dimensional projection of it. And because it's a 3-dimensional projection of a 4-dimensional object, we see here that there's a self-intersection here, which is not meant to be, but because we are living in a 3rd dimension, that's why it's self-intersecting. But if we experience world in the 4th dimension, you know, this what is it called? This intersection won't occur. It should actually all flow through together. So the Klein-Bot is a shadow of a four-dimensional object in our reality right now, which I find very fascinating, and I think it's as artistic merit that could actually be used for very fascinating and interesting things. And so we get back to spins, and there is what you call the Dirac belt trick, which is also something that I feel as very performance, which is very performance based. But I'll play this video.
With my old rusty belt. So with my left wrist, I'm gonna do a 360 rotation. So 1, 2, and this is 360. As you can see, the two ends of the belt are in the same original position, whereas the center is clearly twisted. I'm gonna do now a little trick that will not change the situation of the belt, since it doesn't involve any rotation of the wrists. As you can see, the belt is in the same situation. Let me start over. This time I'm gonna do a double 360 rotation, which means 1, 2, 360, 3, 4, double 360. And let me do again the same trick, but this time the belt is no more.
And so this is what you call the Dirac belt trick, and it tells us that this is exactly what the electron does on the atomic scale. Is an illustration of what the belt does on the atomic scale.
The belt with.
Okay, and this is what you call is a very fascinating animation called air on the Dirac string, which also gives us an intuition for what the electron does. And the reason why I keep bringing, I'm really hammering on the electron, because the electron is, and the spin is a very fundamental part of quantum computing. The spin is what's most convenient to measure.
Paul Adrian Dirac devised a topological trick with strings in order to illustrate graphically an elusive property of the spin of the electron. In quantum mechanics, all particles are connected to each other and to every observer in the universe. For an electron, there is a quantum state or wave function relative to a given observer. If this observer should walk around the electron, making a full turn of 360 degrees, then the wave function changes sign. This means that while a quantum mechanical system involving electrons is not brought back into exact coincidence with itself after it is rotated by 360 degrees, it is brought back into coincidence with itself after it is rotated by 720 degrees. Here is Dirac's visual metaphor performed as the Philippine wine dance. Watch closely how the dancer winds the cup through 360 degrees, acquiring a twist in her arm. Then she winds the cup through another 360 degrees, and the twist in her arm has disappeared. Notice how the ribbon is moving around the inner sphere. The ends of the ribbon do not move. They are fixed to the respective spheres. And yet, now the ribbon returns to its original position and all the twist is gone. This is the Dirac string trick in modern form. We have programmed the computer to twist the space between the spheres. The strings, whether one or many, are located in that space and acquire their twist from the twist of the space. Once we untwist the space, the strings untwist as well, and we have given you a glimpse of quantum mechanical reality.
So yeah, that's here on the Dirac string, and it tells us about how our spin works on the quantum scale, on the quantum level, and how the electron, the wave function of the electron, like I mentioned earlier, the sign flips, so it becomes a negative electron. Which is called a positron. So there's a very fascinating idea of what a positron is, which is by Feynman. So that a positron is an electron moving backwards in time, which I don't think it has been proven or disproven, but it's a really fascinating idea and concept of what the electron or what the positron is. So so let's talk what quantum computing is. So quantum computing is a way of of computing using quantum mechanics, using the principles of quantum mechanics. And compared to our classical computing, it makes use of what you call qubits. Now, qubits are comparative to the classical bits. So in classical computing, right, we have bits. So a bit is either 0 or 1. It can be both. It can't be both at the same time. But a quantum bit or a qubit can live in a superposition of all those of those two states of the 1 and 0 and the at the same time, right? And so let me try something. So we have so for like your classical bit, and why is it powerful, and why it is powerful is because the computational power increases exponentially, right, as the number of qubits increases. So once you are doing whenever you're doing classical computing, right, if we have, let's say, 3 bits, or let's say 2 bits, that's all we have. We can't have more than that. Right, so it could be 1, 1, or let's say 1 and 0, right? Let's say we have those. Okay, let's do 1 and let's say the 1 and 0 bits for classical computing, right? So we have this. But if we for a quantum bit or a qubit, we could have 2 bits called a, and it's notated it's called a Dirac notation, a Ket notation. So we have this here, and so this is 1 qubit, and this is another qubit. And because they can be in this superposition at the same time, we can have 4 possible states. So you can have 1, 1, right? 1, 0, 0, 1, and 0, 0. So that's 4 already. So that's 4. This is just 2, right? So it increases exponentially. The computational power increases exponentially as the number of qubits increases, as compared to the classical bits, whereby it just what you have is what you get, you know. And what the qubit does then is that it gives us a probability of a state being in 1 or 0 when you measure it. So you don't actually get okay, so let me probably bring up this diagram here, so this probably explains it better. Right, so this is the wave function, and we have your alpha and your 0, your qubit 0 and qubit 1, right? And this is the beta. So your alpha is the probability amplitude for 0, and beta is probability amplitude for 1. Like I said, it's measuring probabilities of. So basically, what this means is that what is the probability of a qubit being in 0 states, and what is the probability of this qubit being in a 1 state. Now, these states, like this 0 and 1, they are called observables, and an observable could be anything. But a very popular observable is called the quantum spin, like I mentioned earlier. So let's say this is spin 0 and spin 1. So 0 could be so 0 is actually notated as, I think, down. Yeah, 0 is spin down, usually notated as spin down, but it could be either way. It depends on you. Whilst 1 is notated as spin up, right? So the probability, it's now what's the probability of being in spin or in spin down or spin up, and this probability amplitude, once you get these two together, right, and square them, it becomes 1. The alpha and beta, right, is actually a complex number. So a complex number is a number that has both real and imaginary number. So a complex number is so an imaginary number is I, is denoted as I, and it's equals to the square root of -1, right? So a complex number is basically, let's say, 1 plus I, or 2 plus 3I. So basically, it has a real number and that's a complex number. But the reason why we denote I as -1 as I is because we can't find, there's no square roots of -1 in the real number. So if you do 1 times 1, it's equals to 1. -1 times -1 is also equals to 1. So there's no square root of -1, in the real number. So what happens is that you just keep it as I, and then once you square it, so once you I square, so I square, that's basically you're squaring this, and this cancels this. So the square roots, cancels the square, and so I square is equals to where's my eraser? Okay, sorry. So I square is equals to 1. I square is equals to 1, and so once you square it, it becomes 1, and that's why once you come here, right? Once you come here and you square both amplitudes together, you have a real number, and so it becomes 1. And so this is what you call a quantum circuit. A quantum circuit is basically a way of understanding quantum algorithms, so it makes it more intuitive for you to read. It's kind of like a musical score, and so these are the qubits. This is a 5-qubit system: 1 2 3 4 0 1 2 3 4, and so on. So that's 5-qubit system, and you read from left to right, and so this measurements. So this is you measuring here, and so qubit 0, nothing interesting is going on here. Qubits 1 and 2, that's where something starts getting interesting. So qubit 1 is quantumly entangled to qubit 2. So that's what this plus this thing is called, a control NOT gate or a CX gate. And so that's it. So basically, qubit 1 and qubit 2 are in a state of quantum entanglement. And once they're in a state of, after they be quantumly entangled, there's what you call a poly poly rotation, for instance. Yeah, so basically this means that you are getting the inverse of this qubit. So if the qubit was -1, it becomes +1. That's basically what it means. But that's in simple terms. It's more complex than that, but in simple terms, the H is what you call the Hadamard gates. So all this, let me put the proper names. They are called gates. So this is the X gate, this is the Hadamard H gate, Hadamard gate S, Y, Z gate, T, and other gates. So this is how you read from left to right, and you then measure them. So I would do a quick I'll do a quick illustration of how to use like the quantum computing system that IBM provides. So the first thing that I want to believe we've actually installed Qiskit on our computers. It'd be nice if we have, so we can follow together. But basically what I've done is I've actually created an account on IBM quantum platform, and I have my API token here with me. So what I have to do now is here. Okay, this is my guy here. So what I did now is, so this is the instruction for how to install your quantum circuit, and this was thanks to Alessandro. We saw his picture before, and he helped with this. And so what we can now do is, if you read, this is basically initialization of the scripts. So QC, we are now stating the number of what's it called? The number of qubits you want in our quantum circuit. So this is a 3-qubit circuit. So you can make it a 4-qubit circuit, for instance. And then these are now operations we want to do. So this is let me leave it as 3 first, so I can explain better. So this is a 3-qubit system, and you can see our circuit here. So this is 1 0 1 2, so it's a 3 qubits. Then this is a Hadamard gate, and we're now specifying the qubit you want to operate on. So you want to create an Hadamard gate for the qubit 0, which is this qubit, which is the H gate. All right. Then this control NOT gate, right? So we want to do a control NOT gate or a control NOT or a CX gate, right? So which is basically like we want to do a form of quantum entanglement between two circuits. So basically, this is the main circuit here. This is the main qubit here rather, and we want the qubit 1 to be entangled with qubit 0, and that's what we do here. That's what we are saying here. Then the next thing we now say, okay, now we want qubit 2 to be entangled with qubit 0, and so this is what it means here. And we then do a map draw, and this is what creates. So we can now do more things like, oh, let's increase the number of qubits, let's say to 5, right? And we then say, okay, this is a control NOT gate. Let's do the control NOT for 2. Then let's do a, let's see, QC dots X. Let's do 3. Then let's do QC dots Y. Which is let's do 4. Right. So now let's run this again. And so we've done this now. So this is now we've basically created a quantum circuit with this, right? And so this is a 5 qubit system, and we've said, okay, we want to create another one gate for the qubit, the qubit 3, the third qubit. I want to create an X gate, which is basically, and all these operations are matrix multiplication operations. So depending on whatever operation you are using, it will determine what matrix multiplication is going to happen to the qubits, right? But let me go back a bit, and let me just take it back to how it was before, right? So let me do this back, right? So this is, we then have what you call the observables labels. So your observables are what you want to measure in your quantum computer. So usually like I said, most we want to measure is what you call your spin. And so and the Z, X, and I are ways of denoting spin, whereby Z is a spin in, what direction is Z spinning again? But let me start from I is identity. So I means you're doing nothing to it. So it's basically like you're multiplying by 1, right? X is you, like I said, X is you spinning so that the state, you are creating an inverse of the state. So if it is 1, it becomes -1. That's what you do with X. Your Y is, so there's what you call the state and the phase for a qubit. The phase is like, how a wave has because it's the wave function, so a wave has the phase, right? So depending on how you want to flip it, so it could be in one direction or on another. So the X only flips the X gate only flips the what you call the state. So it has to be up or down, but it doesn't flip the phase, right? While the Y gate flips both the phase and the state, and the Z gate flips the state, the phase. And so what we are doing now is we're just randomly, giving different operations we want to happen to it. And so we load it. So this is correct. And then we then go to this block of the code, right? So like I said, remember we have an IBM token. So from here, this was IBM here. The API token, we are just copying this, right? And we are just pasting here. And it changes, I think it changes like automatically for every month or so, if you don't change it yourself. But you can also manually change your token all the time. And so let's run it. Okay, then now we're doing a service at backend. So block of the code, we want to know what which of their quantum computers is active at that particular moment. So there's IBM backend, IBM Brisbane, Kyoto, Osaka, Sherbrooke. We can also see it here on their platform. Let's see. Okay, so these are the ones I have access to, as you can see. Like I said, Brisbane, Sherbrooke, Osaka, and you can get more information about them here. So there used to be what you call quantum simulators. So a quantum simulator is basically simulating a quantum system where it's not really a quantum computer, but it's just simulating it. So there used to be it until like 3 or 2 months ago, where that IBM discontinued it because they felt that it didn't make sense that they provide as a service, that it's better for groups that you just use the quantum computer directly. I remember when I first started using, I was always using the simulator because when I first started using it, the simulator was always faster because less people were on it. There were more of them, and then if I used the quantum computer itself, it took like, I remember the first doing it, took like 3 hours to get my result back. And it wasn't because it was slow, it was just because there were like many people that were using it. So there's like a queue. So I could be like Q1, I could be like number 1000, and I have to wait for everyone's work to finish before it got to my turn. And so it took many hours for me to get my result back. But I think now with this, I don't know how they've done it, but it's faster now. So yay, IBM. Yeah. Maybe not this guy. So now what we can now do is, let me comment this guy out. We can then decide that, okay, we want to choose the particular backend we want to use, right? And so, like I said, we can see more information about it. So basically, what the information we can get information like how many pending jobs. So these are 17 pending jobs. That's 17 people before you that need to get their job done, before. Then this is 2 jobs. Sherbrooke. So let's note that Sherbrooke is 2 jobs. Osaka is 3 jobs. Kyoto is 58 jobs. That's cool. So let's use Sherbrooke. There's an automatic way of doing it, but let's just use this for demonstration purposes. So I'm just going to copy this guy and paste him here. So Sherbrooke. So I'm initializing it now. So I'm running this code. And okay, so now it tells me, okay, yeah, this works. And let me so as you can see, IBM is IBM. But while it's waiting, let's go on to other things. Let's see, do I introduce this one? Okay, yeah, so a block sphere is how to visualize a qubit. And it's basically how so actually spin up is 0, while spin down is 1. I made a mistake with that, but that's cool. That's how it's usually denoted, and every point on the block sphere is a superposition of these 0 and 1. So if the qubit is precisely at 0, right, this arrow here would actually point directly vertically, right? And that's the result. But if it's at spin 1, it points directly at this 1. While at every state, it's a superposition of these 2 and creates what you call the wave function with this. And this is kind of way of understanding and visualizing it based on what the spherical coordinate system, which so this is theta and phi. Theta and phi is basically the angle. It's the angle with respect to the z-axis, not the z-axis. Okay, let me see. Okay, so it says theta is inclination of angle from the z direction. So this is the z direction. This is 0, 1. So 0, 1. That's the that's theta. While phi is azimuth in x direction. So this is the x direction. So this is the what is the word now? It's rotated around about this vector here, while the theta is rotating about this vector here, right? And yeah, this is just that and some more, but this is more interesting here in the sense of what more can we then visualize, right? Is this done? Okay, yeah, this is done. So 2 minutes 6 seconds. That's good. So let's, and so then it plots our result here, and our result is a probability of all those gates that we talked about earlier, of all those gates, the observables that we plotted earlier. And that's basically this was like the first thing I did, and it felt boring to me. I was like, okay, what can I use this for? What can I use this for? And I was like, okay, I don't think I can use this for anything, but rather than give a good intuition of, okay, this is how to program a quantum computer. This is the result that you get at first. Now, this is what you call a pure state, and a pure state is a simple. It's rather simple. But what happens is that in quantum computing, when you compute, you get what you call a mixed state, and a mixed state shows both the real part and the imaginary part, which is what I'm going to show now. So basically, we are doing the same thing we're doing here. We are initializing the quantum circuit using Qiskit. Then we are plotting the, like I say, we have the visualization package and all like that. So this is QC, quantum circuit 2. So this is a 2-qubit system, and so this is basically a. So let's do something like a CX, right, for both of them. Let's do it, since we already know how to now write, so we can play with it now. So let's do QC dot Z. Let's do 1, right? So, and good thing about Qiskit, that Qiskit is based on Python. So it's, if you know how to program Python, it becomes easier for you. Even though I didn't know how to program Python too, that mine was C#, but it still felt intuitive, you know, in a way. And yeah, so this QC dot Y, let's do 0. Then let's do some sort of quantum entanglement also. QC.cx. Did one, so let's do 0, 1. Okay, no, let's do 1,0 instead. Right, so let's, so now we have our circuit now. We've changed, our circuit has changed already, which is, and it's become more complex. Now the next thing is, let's generate what you call a density matrix, right? So what we're doing, like I said, we're initializing some important things here, and we create what you call a density matrix. A density matrix is basically an array, and it's an array of values. So what we're doing, we're just writing, what is it called? We're just writing like some, let's see. Okay, do I want to use this one? Okay, let me just use this one now. So what I'd done was I had created a CSV file, and I'd gotten some data input, and I'd used that to I'd use that as values for the qubits, right? So, but it's the same thing we are doing per se, but it's the same thing we are doing, right? And so what we are doing, we have our data we got from a CSV file, right? Then we delimiter is our comma and all like that. Then we have our, let's go back here. So our quantum circuit now is data.shape, which is the data.shape, which queries this CSV file that we have here, right? And we have our qubits, which is equal to 1. So So it's asking if our qubit is 1, what should we do to the qubit, right? So for qubits 1, we want to create an Adamant gate for it. For qubits 0, we want to do a control NOT gate for it. For qubits, let's add more. So if qubits is equals to 1, if qubits is equals to 1, QC dot H qubit. So basically, we're creating some rotation data for it. So let's see if qubit is equals to 0. Let's do what we do this with. Let's do a QC dot Z. Yes. Right. And so we're going to create a state vector from the quantum circuit. Then we're going to plot it, and let's see. So what I did here was let me probably just comment this out. Let's play this guy. What's happening? So that's 92. Next updates. Right through this menu. Sure, let me read from here. This is working. Okay, I know what happened. So I need to get this export.csv file, which I had created somewhere else. Where are you at? So because it doesn't know where to get the data from, or better still, what I'll do is I'll create an export.csv file here. So let's do a do I create text? But CSV. So these are like different rotation data, right? So let me just copy out these guys. So since it's a 2-qubit system, I just need 1, 2. So let me open this guy and let me paste something like this here and save. But let me it's not working. I doubt if this will work, but let me check it out. If not, we'll probably have to use okay, yeah, it's working. That's good. Okay, so this since it didn't change, then let me comment out these guys too. That's strange. Why not showing? Real matrix, imaginary matrix. Comment out this, guys. It's the date. That's strange. So usually something is meant to pop up called the quantum density matrix. This is already the quantum density matrix, but there's a plot that usually comes up with it. So I'm trying to understand why it's not coming out. State data. That's strange. It's not showing. I'll have to figure out why it's not, but I think I have like an. So this is kind of what we're doing already. So we are to create a quantum circuit and we have to write the code and everything like that. So this is what it creates. It's called a quantum density matrix. So basically those values that we got are now plotted in this form. And it's one of also those things that I ask physicists that they ask, okay, what exactly does this thing mean? And no one really seems to have a good way of explaining it. And I keep asking, like, what does this mean? What does this mean? I'm like, I can't. Is it like, oh, I don't really know so much per se, or I don't have to explain it. But one thing though is that for the real amplitude, like I said, there's a real amplitude and there's an imaginary amplitude. And so once you go from left to right diagonally, if you add up these values, it always equals. It's always if it's a quantum. If it's a quantum, what's it called? If it's a quantum system, it's always equals to 1. If you add up all these values together in this diagonal line, it's always equal 1. That shows that it's a quantum system, right? And so what I did was, okay, I used the 2-qubit system. Could I use that to then plot like a texture that could be used for something interesting? So I started. So the 2-qubit system, and my friend Emotoyemi Ojewale, he met at MEC, and he actually helped to create a Python script that could then send out the density matrix to form like textures and images that we could use that to as textures for like wallpapers and all of that sort. And so they could use like a blurring algorithm for it. What interesting things will come out of it, you know? Then this was a 2-qubit system. It was the result from a 6-qubit system rather. And I was like, what is this? What is this? And I didn't really like it, but it was like from a 6-qubit system. So what we did was that we got the imaginary values and the real values, these two values, and we sort of use them as a means of plotting the pixels on on a texture. I started thinking, could you also use so this was a 6-qubit system, the result from a 6-qubit system, or could you use that to create some sort of quantum collage that we could use the output each time to now create some sort of collage that would come together and create something interesting, and so I want to also show works from other people who've also done some things in quantum computing in their art, and this was by Idifong. So Idifong was the person I told you that I met earlier in Dublin, and she used what you call quantum noise, and quantum noise was used to create a sound, an audio visual experience basically. And so let me just play this.
Small.
It's like a flower blooming.
Yeah, it's also more than that. It's suddenly sometimes at this like really,
Oh goodness.
it's so yeah, it's hard to predict what it does. Almost never repeat itself.
So no pattern will ever repeat itself.
Supposed to be, this is what they argue, like true randomness should allow like no repetition or anything.
So basically, the quantum noise is the seed for the.
Yeah, the quantum noise is. And I'm still trying to learn. There are so many ways to retrieve the source of randomness.
Okay.
Like, my basic understanding is like the data from the vacuum fluctuation.
Okay.
But some physicists argues like it doesn't.
So you can say that's Edith Fong's work, and so she, like I said, she's using a lot of quantum randomness. Then there's also Lee Biini, an amazing artist and theoretical physicist, and this was a work called Slime Core.
Slime Core is an immersive, performative lecture that uses slime as a metaphor for quantum physics and also the slimy world of big tech. As the time stretches, you pulsate and your collective energy peaks and falls. Fused together, you touch, gliding on slime. Now, the projection has been edited using data from one of IBM's quantum computers. So what I've done with the quantum computer is to create, I think, about 2 million copies of an entangled state. So entanglement is a phenomena that exists that you can create with a quantum computer, because what happens when you have entanglement in a computer is all possible calculations are taking place at once rather than sequentially like on a digital computer. So what I'm doing is using this entanglement to edit the video that you can see behind me. So there's 32 videos all playing at once. And depending on the entangled relations inside the quantum computer, different parts of these videos are shown more predominantly or less predominantly. So they're kind of all these strong relationships between these different videos are coming into being and then decaying, all driven by the data from a quantum computer. Demonstrating fluidity and boundarylessness of so-called individual entities, non-entities. Mucus exploding, unfurling, extending, opening. Slime Core is an immersive, performative lecture that.
Then this is Mikal. So these were some sketches like trying to understand quantum concept. I think this was quantum entanglement. Then this is my project. This is working with Samuel Udo. So I was doing my project about using performance as a way to actually talk about and describe quantum computing and use that as a performance, a quantum computer in some sense to create quantum algorithms. So this was Samuel Udo doing some motion capture for me. And it was also at Pan-Atlantic University, VHCI, Virtual Human Computer Interaction Lab at, Pan-Atlantic University, which is really quite fascinating. So this is Sam. And then what I then decided to do was use the quantum computer for virtual reality, extended reality, and then
èèyàn kò gbàgídí ọ̀pọ̀lọpọ̀ òun àkójẹ ń sinmi ṣe mí jọ́nà tí mi yàtọ̀ sọ́wọ́ kọ́ fami sọ́nà kámi lọ́tọ̀ gbọdọ̀gbọdọ̀. Sit the night for the club, you can go. Ọgbọ́n Sadiq.
Yes, so this was using the mathematics and using what you call vector fields, and using the vector fields to then manipulate the environment around the performer in which would be in virtual reality and or extended reality, because that is mixed up, virtual extended reality, and so this is my work in progress and all like that. And yeah, thank you very much. I hope I didn't bore you guys too much. Yeah, and yes, it was really nice being here. Thank you.
Yes, that's what we are.
Hi everyone. I forgot to ask. Does anyone have questions? I'll try to answer as best as I can, knowing that I'm not a quantum physicist per se, but yeah.
Yeah, that's better. Evening. Damn. Damn.
Yes, I can hear you.
Yeah, so I don't want to say that that part where you gave the two-wave equations. Like, can you
That part
recap
where
that slide? The wave equation, the probability equation. Can you recap that slide?
I didn't get that part.
The probability equation that you gave.
Okay,
Can
okay,
you
okay.
recap that slide?
All right, sure. Let me share my screen. Just 1 minute, please. So if I'm getting right, this was this place, right? That's this screen, right? Okay, so let's recap this part. So for every state of the quantum of a qubit has what you call as what you call a wave function, which is denoted with the psi, right? And it has two parts. It has let's say you're measuring two things. You're measuring spin up, which is 0, and spin down, which is 1. Right now, the alpha and the beta are probability amplitudes. It's like, you know, when you do 3x plus 2y, those kind of things. But instead of a now being, you know, if you say 2x, the coefficient, which is 2, right, is a real number, right? But in this situation, the a and b coefficients of this qubit, of this 0 and 1, the alpha, which is the coefficient of this 0, right? It's not a real number. It's actually what you call it's a complex number. And so I have to go back to the idea of complex numbers, right? And complex numbers being what is called, like let's say 2 plus 3i. It's a complex number, right? Where 3i, that's the imaginary part, right? And so I talked about imaginary numbers, right? So the imaginary number, which is based on I, so I is equals to the square root of minus 1, right? And so if you want to find the square of, hello? Also, if you want to find the square, if you want to find the square rather of I, right? You are basically squaring this and squaring this. So I square is equals to minus 1, right? So now if you are doing like we're talking about the probability of this guy, right? So let's say let's just do like a random complex number, right? So let's do 2. Okay, this is 2 plus 3i, right? So if you want to get the square of 2 plus 3i, right, square, we're going to factorize it, right? That's 2 plus 3i, right? then 2 plus 3i. Right, you're multiplying them together. So 2 times 2 plus 2 times 3i plus 3i times 2. Let me see. I know. Let me see. Plus 3i times 3i. Right. So we have let me see. There's something wrong somewhere. Plus 3i, 6i plus. So this is meant to cancel out. Somewhere it's meant to cancel out. Let's see. Where's meant to cancel out? That's 4 plus. That's where this takes us to. 6i plus 3 times 3i. That's 9, right? 9 times I square. That's minus 1. 9 times minus 1, right? Then let's see. That's strange. Am I missing something somewhere? Why is this 6i not? Why is the I not canceling out? Yeah. Well, let's continue. 4 plus 12i. No, it's meant to cancel somewhere. Or there's meant to be like some subtraction going on somewhere. Plus minus 9. Am I missing something somewhere?
That's the first Please, can you check the charts? There are some comments in the chat.
Okay. Can you imagine that? That's what it's meant to be. No wonder it doesn't canceling out. So it was meant to minus, right? So let's cancel these guys out. Thanks for that. So yeah, it's meant to be minus, yeah. So once you expand now, that's better now. So 2 times 4 plus, yeah, 3i. No, sorry. Plus 2 times 3i plus 3i times 2. Then minus 3i minus 3i. So that's, why am I making a mistake here? So 2 times 2, 4, right? 4 plus 3 times I, that's 6. So it's minus. What is wrong with me here? Right. So so this is minus 6i, right? Plus 6i. So they cancel each other out, right? Then this is minus 3i times 3i. So let's take out this one first. So 3i times 3i, that's 9 times I squared, right? So 4 is equal to 0 minus 9 times I squared, that's 9 times minus 1, right? So it is 4 minus minus 9, then equals to 4 plus 9, then which is equals to 13. So once you expand the complex number, it gives us a real number. So, but the whole idea, therefore, now is that in the end, you always get something like, let's say, 0. 6.2 for, which is the alpha, then the beta will be 0.38. You get what I mean? So once you expand the complex number for each of the sides, so it's, and once you add all of them together, you get it always equals to 1, always equals to 1. So alpha and beta always equals to 1. So whatever it is, so you expanding that complex number gives us a real number, and then because by squaring it, and once you add them together, it becomes 1. I hope you understood that.
Intention when Ife actually finished the intention, and then we were waiting for question and answer. For Nancy, I think he went back for the presentation. Now he's still there.
Hi, Ife. Hi,
Actually, also.
Hi. Are you ready for the question and answer?
Oh, there is asking questions already.
How was it?
Thank you, Ife. Thank you, Ife, for your time.
Science and technology.
I will also create a folder and send all these resources, the slides and the script and everything. So everyone, that'll be. All right.
Thank you for your time. We have so if you're on holiday, you could come by the institute, the library. It's an amazing place with amazing resources, books, and books, text, connect. Anyway, if you have projects you want to have a conversation about, just stop at Goethe Institute Library. We have workshops that are really cool. I think next week will be a 3D printing workshop. And, get through the School of Science, I think, will inform you some more. But you could also follow us on Instagram at GI_Nigeria to see other programs that we have. And yeah, thank you for your time. And I look forward to all you guys create with quantum computing and what you do. Right. And please don't forget to talk with the Dreaming New Worlds artists as well. It's really fun exchanging ideas. Really, what arts do you
We just invite the artists to the stage.